For this example, we want to know how fast the area of a square is increasing when the side length is 3 meters and it is growing at a rate of 0.3 meters per minute. So what shape are we dealing with? A square. And we're dealing with its area versus its side length, right? So we need to find an equation that relates the area of a square to the length of its side. So, what equation do you guys want to use?
S squared.
Area equals what?
S squared.
S squared?
Yes.
Okay, it doesn't matter, but whatever variable we pick there, we're just gonna all use. We could use x squared, we could use s squared, we could use e squared. A lot of people use e for edge, you know. So you'll wanna do s squared?
Yes.
Okay. So we understand what our variables are, how they're related, and what they stand for. So keeping that in mind, let's go back now and see what we were given. We were told that the side length is growing at a rate of what? 0.3 meters per minute. So is that ds dt or dA dt?
Can we say DL dt?
Well, we've already picked s, so we're going to say s. So is it dA or is it ds? It's ds. And be careful, if you're not sure, you look at the units. If it's plane meters, that would measure a side length. It would have to be meters squared for it to be talking about area. It would have to be cubic meters for it to be talking about volume. So if you're not sure which variable you're talking about, look at the units and they will tell you. So we have ds dt is positive because it's increasing 0.3 meters per minute, and we are being asked to find how fast the area is increasing. So we're being asked to find dA dt when what? When s equals 3 meters. Are we good? Okay. So let's just take the derivative of a equals s squared, and the derivative of a is 1 dA dt. And remember that we're taking the derivative with respect to time, and that the derivative of s squared is 2s multiplied by the rate of change of s, so ds dt. So it's with respect to time. Then we look at what we're hoping to find. We're hoping to find dA dt, and we just substitute in quantities for everything else and solve for dA dt. So we have s is 3 meters, and ds dt is 0.3 meters per minute, and that will make what? 1.8. What will my units be? Square meters per minute. And if you put them in, you should be able to track them. Meters times meters is meters squared. If you're not good with the units, don't worry about them until the end. If you don't want to track them as you go, we know that it's area, and so we know it has to be square meters, and we know that it's the time units are minutes, and we know it's a rate, so that's why it has to be a square meters per minute. So that's probably the easiest one we've done so far. Next, we want to take a look at ladder problems. And so here's what we have. We have a ladder that is 20 meters long, and it is leaning against a vertical wall. If the bottom of the ladder is being pushed towards the wall at a rate of 2 meters per second, how quickly is the ladder moving up, like climbing the building, when the base of the ladder is 5 meters from the wall? This is probably the first problem that you really need a picture for it to kind of wrap your brain around. So let's just kind of draw a picture of it. Let's say that here's my building, and here's my ladder. We'll even make it look like a ladder. Okay. And here is flat ground. Okay. So what is the one thing that is going to be constantly true here? That ladder is 20 meters long. We're not expanding the ladder, okay? So we're told that the ladder is 20 meters long, and that's not going to change. So I'm going to go ahead and use that. See this quantity and this quantity? Those aren't constant. Those are going to change. So I need to call them something. So I'm going to call the horizontal x and this one y. So if I think of it like that, and one of two things is going to happen. Either the ladder is going to be moving towards the wall, and that would make it vertically getting higher, or the ladder is going to be pulled away from the wall, in which case the vertical would be getting
Bigger.
smaller if I pull it away, right? Okay, so we need a relationship between these three quantities geometrically. So anyone? Pythagorean theorem, yeah. So let's go ahead and let's say we're going to use that as our equation. We know that x squared plus y squared will always equal 20 meters squared, right? So that really would be x squared plus y squared would equal what? 400. And it is okay to substitute the 400 in now because it's constant, it's not changing. If the latter were also varying in length, like the length was changing as well, then we would have to use another variable there. But because it's going to always be 20 meters, then we're not going to worry about it. Like, you can plug it in beforehand. So far, so good? Okay, so now that we know what to call everything, let's see what we were given. We were told that the ladder is being pushed towards the wall at a rate of 2 meters per second. So is that dx dt or dy dt?
dx dt.
That is dx dt. So we were given that dx dt is, now you have to think about this really hard. Is the x getting smaller or bigger? Smaller. So it is a negative 2 meters per second.
That's a big gap. Wow, that's quick.
No one said it was realistic. Okay, are we good so far?
Yes.
Yes? What are we being asked to find?
dy.
dy dt. dy dt when what?
Y.
Is it when y equals 5 or is it when x equals 5?
X.
It's when x equals 5. It's when the ladder is 5 meters from the wall. So that's this right here. So you really have to kind of dig in and see what's going on. Once we know everything and we've labeled everything and we know what we're hoping to find, we can just take the derivative and plug in what we know and solve for what we don't. Are we good? Okay, so let's look. What is the derivative of x squared?
2x dx dt.
Perfect. 2x dx dt plus, what's the derivative of y squared?
2y dx.
2y dy dt? What's the derivative of 400?
0.
That's what's nice, is that side zeroes out when that ladder is a constant. Now let's plug in what we know and see what's still missing. I know that x is 5. Do I know dx dt? It's negative 2. Do I know y? Not yet. Okay, so I don't know anything there yet. But I'm looking for dy dt, so it's okay for it to be missing. So here's where I am. I thought I had everything I needed, but I don't. In order to find dy dt, I need to know what y is at this moment in time as well. And the way you do that is you know that x is 5 at that moment. And we know that the ladder is 20, right? And this is 5. So you could go find the y value that goes with that x. Sometimes they won't give you everything you need, but you'll have to go back and find something else. So I'm going to pause right here and let you guys find out the value of y when x is 5.
Square root of 370.
So from this situation, we know that this has to obey the law of the Pythagorean theorem, so that 400 has to equal 25 plus y squared. So that would mean that y squared is 375, and y would be the square root of that, or 5 square roots of 15. And it is important to keep things exact until the very end. So we'll plug in 5 square roots of 15 right here, and then we will solve this for dy dt. So we'll just clean it up algebraically. This would be negative what? Negative 20 plus 10 square roots of 15 multiplied by the rate of change of y with respect to time equals 0. So we have 10 square roots of 15 times dy dt must equal 20. So really it looks like dy dt equals 2 over the square root of 15.
Yep.
And we need to put units on. I took them out so that it wouldn't look so busy, but we should be able to figure out what they are. It's a y value, and so that's going to be measured in what for this problem?
Height.
But I need a unit. Meters? Yeah? Meters per what?
Second.
Second. Meters per second. so here is what we think the answer is. We could also turn that into a decimal if you'll give it to me to 3 decimal places. What's 2 divided by the square root of 15?
0.51639.
Okay, so that wraps up that first ladder problem.